Welcome back, ladies and gentlemen. We're going to be continuing now with graphing. So we've done the basic overview of most of the terms that you would have done in grade 10. Now, graphing, for the most part, you did it in grade 10. We're going to take it a little bit further, much like how we took vector addition just a little bit further. So we're going to start off with an overview of graphing in your notes, and then we're going to be going into more detail about position time graphs, which is the first type of graph that you really learned about in grade 10. So if you take a look here, getting out your note page, it talks here about how that graphs are pictures that we use to hunt for patterns in data. Often students forget the purpose of graphs. Graphs help us to understand things, right? Case in point, if I were to take any old piece of paper, like say this page out of your booklet, and on this piece of paper I were to have a bunch of numbers in a chart and just throw them up on screen and then take them down, sure, you could pause the video to quickly take a look at them, but you wouldn't be able to instantly get a picture of what's going on. Conversely, if I do exactly the same thing with a graph and going, boom, there's the graph, put it away, you get a sense of what's happening in that graph very quickly. So the purpose of graphs is to make it easier to interpret information, easier to decipher patterns. Everything that we're doing is about finding patterns. So the reason that graphs work, as it says here, it does this by grouping numbers into shapes that we can identify. We will explore many different types of graphs, but they will all share the same basic shape. Now, the shapes that we're going to be dealing with are going to be flat lines, sloped lines, and curved lines. Now, a flat line, so called because it is flat, will mean that there's no change in the y-axis. A sloped line that goes straight up at an angle means that there is a constant change in the y-axis. This is compared to a curved line, which means that there is a variable change in the y-axis. So it starts off slow, but it gets faster and faster as we go. So each of these shapes, they all mean the same thing, but depending on the type of graph we're looking at, we're going to get different overall trends or different overall meanings. This is the main source of confusion that most grade 10 students have, because you end up looking at things and you're being like, in a position time graph, a flat line meant one thing, but in a velocity time graph that looks very similar, it means something different. And so that causes confusion for students, and it's a common issue. So hopefully with a nice summary here, we'll be able to piece it all together. So we're going to take a look here. We've got that summary. So we're going to have our three types of graph that we're going to be dealing with in grade 11. Yes, three types of graphs. You're going to be having your position time graph. Oops. Yeah, there you go. Position time graph. You're going to have your velocity time graph. And you're going to have your acceleration time graph. And those three are going to have three different shapes, as we just said, right? There's going to be one, option 2, and option 3. Option 3 is a curved line, option 2 is a sloped line, option 1 is a flat line. So there's only three shapes, and there's only three different types of graphs that we're going to study, which means that in total, there are only 9 possible combinations that you have to know. It's actually going to be easier than that. Because, as we're going to see here, right, if there's no change in the y here, that means that for a dt graph, v equals 0. For this one, the velocity will equal some number, depends on the exact context, and here the velocity will equal a changing number. Now, the reason why it's velocity is what I'm talking about here, despite the fact that this is position, is because you may remember that the slope of a position time graph is velocity. If you don't remember that, don't worry about it too much. This is an overview. We're going to go into it in detail once we get into that particular section of the notes. So let's continue. That is v. Then we've got, on a velocity time graph, acceleration is 0 if it is flat. The acceleration is a number if it is sloped, and the acceleration is a changing number if it is curved. There's a pattern here. So for the acceleration graph, there is another term which you may not have heard before. It is, of course, called jerk. Acceleration is change in velocity. So if you're sitting in a car and the car is going back and forth a lot and it's really knocking you around, you're getting jerked around. So jerk is what this is called. In this case, jerk would be 0. Here, just like before, it's a single number. And here, it is a changing number. So as you can clearly tell, there's a very specific pattern that we're dealing with. But here's the wonderful thing. You don't actually have to deal with all 9. I said under normal circumstances, there's 3 types of graphs, 3 types of shapes, so there'd be 9 that you have to deal with. But you don't. You don't have to deal with all 9. I am not going to require it, neither does the course, because for all intensive purposes, we do not deal with all of these. All of these are not covered in grade 11. So these can be removed from our list. That's very convenient for us because, well, I mean, it went from being 9 things we have to do to being 6 things we have to do. And you'll notice that the acceleration graph here has literally 1 thing. So the acceleration graphs are incredibly simple, but we'll have to get to those eventually. So this is the overall summary. These are the things that we're going to have to deal with. With that in mind, let's take a look at position time graphs in detail. And remember, we're always trying to look for the shapes and to understand the pattern behind those shapes. So, as the notes tell you, flipping it over here, position time graphs. A position time graph marks the position of an object compared to a reference point. So the purpose of a position time graph, let's leave that up. The purpose of a position time graph is to tell you where something is with respect to something else. So for example, right now, if I had this marker basket as my reference point, I could say that this eraser is now a certain distance away. If I wanted to measure it in meters, I could do that. And I could say, okay, let's take out my meter stick. I put it down here, and I will see that I put it exactly 64 centimeters away. So there we go. This is 64 centimeters away from a reference point. Now, in this particular case, it's to the right, which means it would be positive 64. And we could graph that along with all sorts of other motions and positions. All stuff that you guys hopefully remember. Now, it says here that in physics, positive and negative means direction. So a positive displacement means I'm on the right of the reference point. And a negative displacement means I'm on the left of the reference point. So I'd have to be over there somewhere. So this is basically what we're dealing with. And if I draw a real quick graph here, just for us to have something to talk about. So here we go. We're going to have ourselves a position. And here's our time. And we're going to do just a real quick and simple one. I'm just going to sketch it. It's not going to be anything with real numbers, at least not at first here. And we're going to go like so, and let's see, how did I do it? Yeah, okay, I kept going. And then I'm going to do something like that. Okay, so we've got all sorts, and we kept going, that's right. Like so. So once again, here's a graph. There's no numbers to it, but we've got a bunch of shapes. And we're going to try and see if we can't follow the shapes and understand what's going on. Now, the 3 shapes, as we said here, can be broken down into what they mean. All right, so let's put this guy back. So flat lines means that the velocity is 0. So right here, we can clearly see we have a flat line. So right here, the velocity is 0. And realistically, if you think about that, that makes sense, right? Because the position here is constant, right? Like if this was, say, the 64 centimeters that we had put the eraser at, this object is staying in exactly the same place for this whole stretch of time. Well, if you stay in the same place for an extended period of time, by definition, that means you're not moving. So that sort of checks out. Then you've got sloped lines where you're moving constant. So we've got two different slope lines and you're moving constant for both of them. So these are sloped lines. So here your velocity is going to be just a single number. Okay, that's pretty straightforward. Then we've got our curved lines where you're going to be either speeding up or slowing down. Your velocity is a changing number, right? And if you've got a changing velocity, that's acceleration. So here in this area and in this area, we're going to have some kind of changing velocity. So instead of saying velocity, we could talk about acceleration. Now, we could mention it at least, but unfortunately we have no real ability to calculate acceleration, at least not directly off of one of these graphs. We will work with acceleration in other graphs, but not in these cases. But that doesn't mean that we can't know if we see a curved one that there is some kind of acceleration. Now, the key thing about all of this is it is built on the idea that the velocity is equal to the slope. Why is the velocity equal to the slope in this context? Well, the slope equation, which you guys originally learned way back in the day, was probably something that looked like this. That's what you probably learned. Probably grade 7 is when it first came up. And of course, the big problem was that people would almost always put the numbers in the wrong places. But here's the weird thing. y2 minus y1, we've seen that before. Like if I rewrite that as, say, t2 minus t1, that is something that we have in our notes. This means something of significance. It means delta t. We could actually rewrite y2 minus y1, x2 minus x1 into delta y over delta x. Now this is significant for two reasons. Because first of all, it's less to write down, and second of all, remember the triangle is pronounced, or if you want to say it, you could say delta y, but you can also say change in y. And that's the definition of a slope. Slope is the change in the rise divided by the change in the run, the change in the up and down versus compared to the change in the left and right. Well, that's literally what this says. Change in y divided by change in x, or change in y over change in x. So the definition of slope actually tells you its formula if you understand delta. The problem is when we first taught you guys slope back in the day, you didn't know what Greek letters were yet. So, things were a little bit tricky. Now, why is this important? Well, for our particular graph, our delta y is d. So we would replace y with d arrow. So we would get delta d over, and our x is t, delta t. All of these are equal, and that means all of this is equal to velocity, because delta d divided by delta t is the definition of velocity. That is what we use to define something as having a velocity. It's displacement divided by the time it takes for it to happen. So what we're seeing here is hopefully some pretty familiar things, but maybe we want to try and work on some details, work on some numbers in some way. What we're going to see if, let's say, I put some numbers into this particular equation here, right? We've got a graph. Let's toss some numbers on here. So I lost my green. So let's pretend that up here is, say, 10. We're going to make this spot here 10 positive. So that would make down here about -8. We'll say this is about 5 seconds. This will make 10. That means this one over here will be 15. This one here will be maybe 12. Okay. So when we're trying to work out the velocity here, it's all slope all the time. When it comes to doing a slope, It's y2 minus y1, x2 minus x1. So y2, let's say the slope for this first section here, section 1. So section 1, we're going to be getting something to the effect of the y is 10, so 10 minus, and the 5 is x, so that's going to be over 5. So remember, right, both of these are for the second point. The first point in this case is very easy because it's just 0 over 0. Well, that's pretty straightforward. So this whole thing is just going to be 2 meters per second. We done? We are not. Remember, velocity is a vector, so we need a direction. So in this case, we could make the direction plus. Okay, that one's pretty easy. Similar, 2 is really easy. Section 2 of this graph is just going to be velocity equals 0 because it's a flat line. Sometimes my grade 10s will call it a dead line because it doesn't do anything. Now we've got the velocity of section 3. Oh, but I crossed the axis. Is that going to make a huge change? No, actually, it doesn't make any change at all. My final point at the bottom there we said was negative 15, negative 8. So section 3, negative 15 is my, 15 is my time, divided by negative 8 is my y, so my final position. My initial position was plus 10, and it was at 10 seconds. So negative 8 minus positive 10, we're going to get negative 18 over 5. Numbers aren't quite so nice, but pull out our trusty calculator, get ourselves a decimal out of that. We could have left it as a fraction, of course. Like, it's not the end of the world. 18 divided by 5 equals 3.5. So in this section here, we are at 3.5 meters per second. Did I get 5 or did I get 0.6? 0.6. I was rounding, apparently. 3.6 meters per second. Now, we're not done, of course. We need to know if it's positive or negative. And in this case here, it is negative because it is a negative slope, right? Positive slopes go this way, up towards the right. Negative slopes go down towards the right. So this one here is going to be negative. Now, what do we do for the curve? Curves are tricky. And the reason it's tricky is because we don't have calculus. So as a result of that, we have to use some approximations, some tools and tricks to get an answer that is at least reasonable. And the two tricks that we're going to use in order to do this, the first one is called a chord. This I ended up confusing with the second one, which is called a tangent. Now, they both basically do the same thing for the purposes of our graph here. They're both going to find velocity. The difference is that a chord will find the average velocity, and a tangent will find the instantaneous velocity. Ooh, do we remember those terms from earlier on? So velocity average is this one, whereas velocity instant is this one. So an average velocity is the velocity across a range, whereas the instant velocity, or the instantaneous velocity, is the velocity right now. What does this mean for our purposes? Well, it basically means that if we take a look at the curve that I've got over there, and we just sort of blow it up a little bit to make it bigger. So we've got our curve, and it sort of does something basically like this. A chord is what happens when I take my deer ruler, and I take it from any 2 points of my choosing. In this case, the 2 end points of my curve. And I connect these two with this chord as an approximation of that curve. What I'm basically trying to say is that I'm sort of looking at that going, the green line is going to be complicated. You know what I'm going to do? I'm going to pretend that the green line is the blue line, and then just use my slope calculation just like I have before. So if a particular question asks you to find the average velocity between 2 times or 2 points, you just draw a connecting line between those 2 points and figure out what the answer is. Put another way, this line here represents what I would have to use for velocity, what velocity I would need in order to get from here to there without changing along the way. The green curve starts off slow and speeds up. But if I start off really slow and speed up, I will get here at exactly the same time as the guy who just ran at a nice jog the entire way. Now, in terms of how you do this, as simple as these, right? So if we assign some values to this point, I'm just going to make up some numbers here. This is all made up numbers in the notes here. So I'm going to say here that this point right here is 1, 1, and I'm going to say that this point up here I decided was 8, 4. Okay, obviously I'm just making up these numbers as an example because, like, realistically that doesn't match the graph that we had drawn earlier on. So we'd have these points here, and how do we use them? Exactly the same way as when we were doing the slope before. So we would go slope is equal to change in y, so the y over here is going to be 4, that's the final, minus the initial, which is 1, all over the x and final, which is 8 minus 1. You put that together and you solve it, and you're going to get 0.42 meters per second, and it's positive. So obviously, the big problem with this is that it's really inaccurate. Like, obviously, the blue line is not even close to the green one. So if you were taking, bets on how accurate using this blue line to represent this green line was, I wouldn't go put any money on it. Now, this is part of what I originally talked about in the video before. The reason it's so inaccurate is because I'm trying to use one line that is straight to describe a curved line, and that doesn't really work. I can improve it, though, because instead of doing one line, I could do 2 lines. I could take my ruler and cut this curve into 2 segments instead of 1 segment. The advantage of doing this is that now I think you can see those 2 lines are going to look a lot closer to the green line. I mean, they're still pretty far off, especially this lower one, but they're definitely closer. And I can take it one step further. If I pull out some red here, I can cut it again. So instead of it being cut into 2 sections, I've cut it into 4 sections. So now when I do this, I go from the end to that first cut. I go from that first cut to the middle. And I go from the middle to the second of the new cuts. Oh, I erased some things along the way. Getting the line here is just so. And then finally, I go like so. Now I think you can see, or I hope you can, that the red lines that I've drawn are much, much closer to the green line that I started with. And this is for the very simple reason that this is kind of how calculus actually works. We take a curve and we imagine that it is increasingly smaller and smaller straight lines all coming together to map this. The more times I cut this, the closer I would get my straight lines to match the shape of the curve itself, which is awesome, except it also increases the amount of work I have to do, right? The blue line that I started with, the one that went across the whole length, that was 1 slope calculation. These blue lines here would be 2 slope calculations. The red lines now are 4. I don't want to do that much work. You don't want to do that much work. So for the purposes of average velocity, we usually just use 1 line and call it a day because it just makes things a lot easier. So that's the first part. If you're trying to find average velocity, you're going to use what's called a chord, basically a line that connects the start to the end. Okay, so that's the first one, and this explanation was part of the original explanation. So what was I confusing it with? I was confusing it with the idea called a tangent line. The tangent line is for finding the instantaneous velocity. So once again, we're going to quickly sketch out here a section of the curve. It comes up like so. Rather than asking about what's the average velocity across this whole range, what a tangent line is used for is finding out what's the velocity right here, or right here, or right there, or really any one spot of your choice. You choose a spot, you want to know what the velocity is there, how are we going to do it? We're going to do a tangent line. The way you do a tangent line is that you're going to take a ruler of some form, you're going to choose the spot you want to find, and you are going to put that ruler on that spot so it only touches that spot and nothing else. The line that you're going to make is going to have roughly the same sign as the curve you're dealing with. So for example, this curve is predominantly a positive curve going this way. So I shouldn't put my ruler like this, because that's clearly going down. So I want something that is positive. So let's say I want to use this triangle one here. I just go like so, and I can make my tangent line as long as I want. Okay, so there we go. I've now made a tangent line. Awesome. And I'm going to use it to find that one spot. So usually at this point what you do is you look down the length of the line and you find some location where you can easily get coordinate information. So for example, the one that I have here in my notes, I'm going to say that this one here is 6, 5. And then there's another one way over here somewhere that's like 2, 2. Now, that's the ones that I came up with in my notes. Realistically, given what I've drawn here, that doesn't really match. So you know what? Let's change our drawing a little bit just to make sure that it's clear. The one in the notes looks something more like this. And I was looking for a spot somewhere in the middle, so we'll choose there. All right, this way it'll be more consistent. So I take my tangent line, I draw it as big as I want. I can make it tiny, I can make it huge, don't care. Then I'm going to find two spots. So I'm going to say this spot up here is the 6, 5 that I was talking about earlier. And I'm going to say this spot down here is a 2, 2. So now that I've got a line that touches only here, I can do a slope calculation, just like I did before. And I'm going to get, 5 minus 2 over 6 minus 2. And I'm going to solve for that. And it's going to tell me that it's 0.75 meters per second, positive. This velocity, we then use the tangent line to say this velocity is the instantaneous velocity at that spot. Similar, we said that this velocity here was the average velocity across this whole range. So that was the part that I managed to get a little bit goofed up. A tangent line and a chord do basically the same thing. They are ways to find velocities for a curved segment. But a tangent line is to find one specific velocity. I want to know the velocity right there and only right there. I don't care about the rest of it. I could do there, I could do there, I could do there, I could do there. I don't care. I draw a line. So you're going to need a ruler. A chord is what we say when we're going to find the average. And so we take something and goes all the way across from start to finish. So there you go. Hopefully that makes a lot more sense now. You guys can continue practicing and working on some stuff there. And I will see you guys next time.